Hi everyone, I'm Zhang from University of Twente, ITC faculty. It's my pleasure to give the presentation about my research in InSAR spatial temporal baseline network construction and comparison, which is accomplished with the help of Dr. Zhang. As we know, the geometric and the temporal decorrelation impact the quality of InSAR pairs and make interferometric information ambiguous. Many tailor-made spatial temporal baseline networks have been proposed and demonstrated in order to obtain meaningful and reliable InSAR time series products, such as deformation time series per InSAR element point. However, a cross-assessment and comparison among those spatial temporal baseline networks are not fully explored. Therefore, this study attempts to design and demonstrate appropriate methods to estimate, assess, and compare InSAR products with different baseline networks. Then we propose a method, and the processing basically includes three parts: real data pre-processing, time series processing, and optimization. After real data pre-processing, we will select 6 different baseline networks here. First, single master baseline network will choose a master image, then all the other images are regarded as slave images and will be connected with the master image. For the short temporal baseline network, we will connect all the images in time sequence, regardless of the spatial baseline. For the minimal span tree baseline network, we use the coherence between two SLC images as a distance and connect all the images with a minimum distance summation. For the minimum number connection baseline network, we will set a coherence threshold first. All the SLC pairs with a bigger coherence will be connected. For the redundant baseline network, we will connect the SLC images as small as possible. For the traveling salesman problem baseline network, we also use a coherence as a distance, and all the SLC images will be connected and only will be connected twice. And finally, the total distance should be minimum. When the baseline network is determined, we will have the time series processing and get the time series deformation results. We use posterior variance to assess the precision and double phase validation to derive the accuracy. Combined with computation load, we propose an equation of the performance metric of baseline networks GK, which is the distance between the target and the original point. Smaller the distance, the better result. Then we could get the optimized baseline network. Then our test site is located in Beijing, China. 21 teraSAR XSAR data in strip map and HH mode acquired from this time period were used. The total area of the experiment is over 200 km square. The leveling data obtained at 2 benchmarks were employed in same time span. In result part, we processed the 21 teraSAR X images with 6 baseline networks with stamps. The minimum number of InSAR element points is over 7,000 to ensure the InSAR products with the 6 baseline networks are comparable. We downsampled every InSAR element point on a common resolution cell size level. All deformation time series were aligned with regard to the manually selected common reference point in the black 5 star in Figure 3. The barycenter assessment results show that traveling salesman problem has a minimum GK value of 0.35, while SM, ST, MST, MNC, and redundant have the values here respectively. As a conclusion, using the barycenter assessment, we found that the traveling salesman problem is an optimized baseline network. Since it is seldom employed, we keep evaluating the performance of the barycenter assessment by applying it to several other test sites. This is my presentation. Thanks for your listening.